Good evening.
Hello, ma'am. Good evening.
Yeah, so I'm audible, right? Okay.
Man, this the week 8 topics is finding difficulty to understand. So can you uh, help us to get some flow? Means the subject. There are multiple concepts was
I
discussed in
I
the
can
lecture.
hear two of you speaking, and I am not able to make out.
Sorry, ma'am, you are not hearing me.
Swastika is also unmuted, so I'm not able to hear. Can you please one at a time? Right now, tell me.
Ma'am, I was saying that lecture 8, week 8 session, is a new concept, many new concept actually. Finding difficult to solve the assignment also. We can means give some uh, flow of the thing. Means there is one is contradicting to another. It seems to me. I'm finding difficulty that concepts.
Okay, okay. So, I mean, week 7, we started with learning BJT, where we had seen that voltage divider biasing. And in week 8, mainly we will be seeing that extending of that DC
Line.
analysis, where we start with the discussion of small signal analysis, so that we talk about the common emitter amplifier. The same thing we will see with the other two configurations as well, common base and common collector. And if I remember correct, assignment questions mainly cover only the common emitter configuration for making you comfortable, because that is the common one. Although we see in the lectures common base and common collector, then one another main topic dealt, two other main topics dealt in the week 8 lecture videos are the concept of differential amplifier and the current mirror circuit.
Right. All are new concept. And uh, solving problem is actually mainly coming difficult. Today is a date. I just could solve just two problems. Mostly concept, I think it's not getting clear from the lecture.
Yeah, we will do some. Today being again is a session on week 8. We will do problems on this common emitter amplifier, then current mirror, and the differential amplifier. Okay. Wait a minute. Yeah, okay. So we can just try to understand the numerical problems on week 8. I will just do some problems today. And maybe Shin chat has put that, yeah, in the current mirror, I reference is exactly equal to I naught without any error. That will be exactly equal only, as you say, in the case of beta equal to infinity. And this is the thing that if you had seen that, if you try to recollect that current mirror lecture also, you can see that when the mirroring stages increases, you will have some error in the mirrored current. So if it is the 10 milliampere that needs to be mirrored, then as the number of replicating stages, the mirroring stages increases, you will have that mirrored current reducing in value. You will have some decimal variations like 9.98 milliampere, something like that, in place of 10. So this point has been even discussed in the lecture, if you remember. Maybe. So as you say, it is the ideal case when beta equal to infinity, and this error also has been discussed in the lecture. And I think in practice assignment or graded assignment also, this aspect has been covered through one question. See, generally, right now, talking, clearing the doubt of Rahul, the need for current biasing. By biasing, we set the DC current and DC voltages in the circuit. So first, a BJT, NPN BJT will function as an amplifier when it is operated in which region?
Active region.
You have even forward active region and reverse active region. So you have the cutoff region, forward active region, reverse active region, and the saturation region. So emitter based junction is forward biased and collector based junction is reverse biased, is our forward active region. And if it is the other way out, that will be the reverse active region. And if both are in the reverse bias, that is the cutoff, and if both are in the forward bias, that is the saturation. And cutoff region and saturation region are mainly used for making transistor function as a switch, open switch and close switch. In the saturation region it will be close switch, and in the cutoff region it will act as a open switch. So we through the lecture videos, we generally focus on the forward active region, trying to design a BJT amplifier. That again, the three configurations are dealt through the lecture videos, and as of now through the assignments also, we have covered, or we have given main focus on the common emitter configuration. So common emitter configuration, common base and common collector, the fundamental difference is what common emitter configuration, to which terminal the input is fed.
Input is given through the base.
Yeah, so common emitter means to the base the input is fed, and as the name suggests, the emitter is common to the input and output, and from the collector the output is taken. Similarly, common base terminal is common between input and output, so it is to the emitter terminal the input is fed, and from the collector terminal the output is taken. And common collector terminal is common, and to the base input is fed, and from the emitter the output is taken. And common emitter configuration, so these things you need to know, as well as common emitter configuration. It is basically a inverting amplifier. That means there will be a phase shift of 180 degrees with respect to the input and the amplified output. Common base is basically a non-inverting amplifier. And common collector, again, although you will not see in detail what about the input resistance, output resistance, comparison, etc., between these three configurations, but generally you understand common emitter is an inverting amplifier, common base non-inverting, and common collector, you can see that it has got unity gain, so it is generally used as a buffer. Those key things you should know. So whatever be the configuration, by means of biasing, make sure that to function a BJT as an amplifier, you operate it in the forward active region. That means the emitter based junction should be forward biased and collector based junction should be reverse biased. So those potentials of those emitter terminal based terminal should be such that the emitter based junction is forward biased. Similarly, collector based junction is reverse biased. Then, so that is properly ensured by properly designing the values for that resistors R1 and R2, the voltage divider resistors, then the collector resistance, emitter resistance. Okay, so those values properly chosen, so that the operating point is it is in the forward active region to function as an amplifier. So that is the key thing. Now, moving to the small signal analysis, what we know is right now we are going to design the amplifier. So this biasing helps us to set the DC voltages and DC currents in the circuit. Now, to the base, if we are considering the common emitter configuration, to the base terminal we are going to feed the AC signal, the small signal. The amplified version of that we need at the output. Okay, so if you try to recollect that analysis done in the lectures, we had seen initially that capital V subscript BE plus VBE, that means this one, this is the DC and this is the signal. Okay, so actually this is the small signal that we need to amplify. So you will have at the output DC component as well, but we are concerned with only the exactly the amplified version of the signal. No DC components needed, but although the DC values are required for setting the transistor in the forward active region. That's why in order to get rid of the DC component from the output, we are using the coupling capacitor at the output. So role of the coupling capacitors at the input and the output, and the emitter bypass capacitor. Yes, tell me, Arnab.
Ma'am, capital VB is the knee voltage sometimes in the transistor, and
Sorry?
VB also capital VB, V capital B. That is knee voltage. Sometimes it is referred in lecture, and it is also DC voltage. Also, when it's supply voltage DC means
Yeah,
what is
yeah. Actually, the NPN BJT, that knee voltage is actually around some 0.6 to 0.7 VBE. That means
Hmm.
for in order to turn on the transistor, that is the voltage required. And this VBE is, I mean, the DC value itself, the same notation that has been,
Same notation. Okay, but they are different, right?
yeah,
Okay,
different in the sense,
it is
I
DC
mean,
supply.
this it should be some 0.7 value above 0.7.
Hmm. Okay.
This DC, no, this VBE will be 0.7 or above that in taking in general the DC value.
Okay. Okay.
Um, okay,
Hmm.
the coupling capacitor connected at the output side, that means to the collector terminal, make sure that it eliminates the DC component of the output, so that we get only the amplified version of the signal. Why do we refer it as the small signal? Because we can possibly design the transistor to get an output of the order of few volts, so that your input signal will be of the order of some millivolts, 100 millivolt or something, so that the amplification factor of the amplifier, I mean, if you try to recollect what you had seen in week 6 of your ESTC, we had just seen something like this, and an amplification factor A. So input is given, this is amplification factor A, means V naught will be AVI, that we had seen. And here, so this was just the abstract idea of that, and this triangle symbol represents an amplifier with designed using the operational amplifiers. This operational amplifier you will learn it in detail in your higher term. Now here we are designing it using the not the operational amplifier but the BJT, using the BJT, and by means of this bias resistors we are trying to design a common emitter amplifier. Okay, so you have the NPN BJT, then the bias resistors R1 and R2, RC, RE. This much you had seen even in your week 7. So you have that power supply. And we had seen that DC analysis also. How do you calculate this? By Thevenizing the circuit, you calculate that what to say, the base current, then IC is beta IB, then you finding out VCE, all such things you right now know. And now to the same circuit we have a few more components. So this is CB, CC, and CE. And what should be the value of these capacitors ideally?
Too small, ma'am.
How about the impedance of these capacitors? It should be
Very less.
Too small.
impedance should be too small. You know that the impedance or the capacitive reactance is inversely proportional to C, right? So you are telling capacitance value also too small and the impedance also too small.
No,
Capacitance
capacitance
will be
value
high,
should be very high.
Ah.
so resistance will be dominant there.
So this so here only we are feeding the input. Okay, so that will have the DC as well as this signal component, which is the AC, to be amplified. So these two capacitors CB and CC, the input coupling capacitor and the output coupling capacitor, are for the that avoid that DC, and this also, this is bypass the AC, this emitter bypass capacitor connected at the emitter. Okay, so now this is a inverting amplifier, and can you just tell me what is the output obtained here? If this is small vi, this small v naught after the coupling capacitor CC, what was that?
Ma'am, just this
Minus GMRC.
Minus GM RC VI. So minus indicates it is the inverting amplifier. So there is a phase shift of 180 degree between the input and output. And GM, what is that?
IEC DC upon VT.
What is that? What is that parameter?
IC DC upon VT.
IC upon VT. Okay, what is that parameter referred as?
Transconductance.
Transconductance. Why it is called transconductance?
Because it is opposite of conductance. Is it something like that?
What is conductance?
Conductance is reverse the resistance. Well, means it's allowed to pass the current.
Yeah. So I, it is a ratio of I by V. So your output current is IC, and here what is this VT?
Thermal voltage.
VT will be thermal voltage KT by Q, and what is the value?
It will be approx to 25 millivolt in
Yeah,
room temperature.
around 25 millivolt. So GM is the transconductance. So this is your this RC. So what do you get after eliminating that DC component of the output? That means I am not asking the output at this point. At this point, what is the difference here? Means you will have the output having both the DC and AC components. Once it passes through this coupling capacitor, you will have only the signal part at this terminal. Okay, once it passes through this capacitor, so that will be this V naught will be minus GMRC VI. So the small signal gain is this minus GM RC. Okay. Then what else you had learned? Yeah, GMS IC by VT. Then any tell me, Arnab.
Ma'am, if there is any additional resistance after capacitor, that will be part of the RC, means the output load resistance will be. If we add any additional resistance,
If you have a load resistance, I think you have one such question in the assignment,
yes,
right?
yes,
So that, yeah, that will be minus GM RC parallel RL.
RC and RL parallel. Okay, so load resistance will be combined of that.
But yeah, how it becomes RC parallel RL? Is it clear?
No, ma'am.
Because once you consider the AC part, just like superposition, you ground this VCC, correct? So that RC and RL becomes parallel.
Okay, VC if we okay, VC if we grounded, then
Correct. VCC will be grounded. I mean, just as discussed in the lecture, you will be doing superposition. When we are considering AC, we set the DC to be 0. So VCC is set to 0. So you will have this from the collector terminal, RC is connected to ground because VCC is now set to 0. Similarly, RL also no, it is connected between this terminal and ground. So RC becomes parallel RL. So it becomes minus GM RC parallel RL in that case.
Okay. Got it. No.
So
Can you repeat it again?
oh, no, he was asking with reference to an assignment question where you have the case of load resistance also. In that, asking for the small signal gain. So there, we are asking about the small. We are talking about the small signal gain. That means only the signal part we want. So we are setting the DC to be 0. That means I set this VCC to be equal to 0. So once while doing the AC analysis or the small signal analysis, when I set DC to be 0, I will have, since here RC, it is connected between the collector terminal and to the supply point. Now once this is made 0, it is like RC is connected between the collector terminal and ground, and already you have a load resistor there connected between the collector terminal and ground. So in that case you will have parallel combination of RC and RL. So in that case it will be minus GM RC parallel RL, the will be the small signal voltage gain. This is with reference to one of the assignment questions which he was asking.
Okay, ma'am, I have one question. When a AC voltage pass through CE, then where it will go?
This is the bypass capacitor. You're asking this bypass capacitor CE?
Yes, ma'am. It
That
gets
is the
short
bypass the
circuit, right?
AC.
It gets short circuit, then voltage pass through it, right? Then where that voltage go?
How will it be short circuited?
Because impedance gets too low.
Impedance is too low. Can you just come to that point again?
Uh,
What happens? Is it the impedance too low or is it to be high?
Impedance is too low. Then it acts like uh, volt short circuit. Then AC voltage pass through it.
Correct.
So that AC voltage, where does it go? Is it go to output VO, like where that wire will go?
I don't understand exactly what is your doubt. Where will it go means? Can you just try to say your doubt in some other words? I don't understand actually.
Like that voltage will pass through CE. Okay.
Yeah.
Then that voltage have to go
Ground.
somewhere, right? Agar if we want V output, then it should be connected somewhere related to V.
V out is here, no collector terminal. And why are you
Why
talking about
is
for
V
V out emitter
in?
terminal? V out is here, correct?
Okay.
Collector terminal.
I just want to ask, like, when that voltage will pass through that CE bypassing a volt capacitor,
Hmm.
then that voltage, where does it go? If that will go in ground, then what's the use of doing that?
See, there's.
Ma'am,
Wait a
may I?
minute. Tell me.
Ma'am, if we are going to complete the circuit, the ground terminal is connected with the VCC. It's making a loop.
Yes.
So it's continuously moving as a circuit, closed circuit. If you are closing the circuit, then you will realize where it is going.
See, actually, if you have a drop, no, in this RE emitter resistance, the gain will decrease. Correct? AC gain.
Okay.
So we should we should make this RE what to say, dummy. Like if you make it this AC to pass through this, there will it will this coupling by making use of this coupling capacitor CE, you can actually increase the AC gain of the amplifier.
Yes, ma'am.
That's the role of CE. That is your doubt, right?
No, ma'am, but it's okay.
I think you are not convinced. Can you just tell me once again, or you just put it in some other
Like that
word?
voltage will pass through CE. Okay, ma'am.
Yeah,
Then it gets connected to some other device, or it connects to some node, so that we can get a V output or something different.
yeah.
That's my question.
Okay, so now the remaining session, can you just tell me if you want me to discuss, go through the topics of week 8 conceptually, or you want me to go through the practice assignment questions, so that any doubts in that, if it is clear, you can do the graded, in which way you want.
Go through the practice, ma'am.
Go through the lectures, is Rahul saying, and two of you are in the chat has put the mentioning like practice assignment. What about others?
Ma'am, practice as an assignment.
I think problem-oriented discussion and resolve the queries there from it will be helpful. Maybe the same
Yes.
problem, different possibilities option, right? Sometimes we can need the resistance. We can assume. I find
The
difficulty the
week 8
problem
practice
solving.
assignment PDF is already available to you on the portal.
Yes, that practice assignment, yes. But problem is that in the same dimension, same configuration. Just if you add the resistance, just sometimes its capacity, it makes confusion. Is how it get may change. Maybe concept of not clear. So maybe single any problem if we start with, and the same problem if we connect different option, and then how it may get changed, the solution, how we can reach
Yeah,
like
that
this.
we can. Yeah, that we can do. So since the practice solution PDF is already shared to you, I think I thought that it was not shared, and that's why you are finding it difficult. So if it is already shared with you,
Yes, it
better
is.
you go through that, and through that you try to submit the assignment. And again, in this session, the remaining time we can devote like taking. Let us do problems on this common emitter configuration, then the basic current mirror, then as somebody was asking in the chat, no, maybe I think as the number of stages increases, how that error in the mirrored current takes place. Those key things we can do. Then and another important topic is that differential amplifier. Okay, so that we can do.
Right, ma'am. Another thing, just think that like same problem what you're discussing now. Let's if we delete the first two resistance, the which is in series on the left side, which for the voltage dividers, just to supply the voltage sum to the base. If we
Yes.
don't remove that, how the problem will get changed? That they are getting confusion. Like it's
No,
same
no.
problem for
Which
different.
one you are telling? Which one you are
The left
telling?
the left side two verticals resistance.
R1 and R2.
Right. If we remove that, just if we the supply voltage, uh, how they typically, if we include the VB now, not that capital VB, just point 0.7, and
Okay.
it means same problem if different option introduce, how the problem solution can get changed. I
You
mean,
are telling that without R1 and R2 means you have a RB there, correct? The
right,
one
RB
which was
here,
similar, one which was discussed in the week 7 lecture, correct?
right, yes. If it is beta large now, or if it is beta is
No, no, that
small,
the same. See, that is the same thing actually. The one that you had seen in week 7 and this one, the fundamental difference is
same.
the biasing. I mean, there we had something like here. If this is the one you're talking about, let me know. VCC, RC. Then here we had some RB and VB. Then RE, correct?
Right, right.
Here we talked about This circuit was part of week 7, where we had discussed that this VB will be less than this VCC. Okay, so in that understanding that point, we need not use, if you see this particular circuit as such, while you make it in the lab, you have to use one power supply for this VB and one another for VCC. So now, since VB will be less than VCC, we make it in the sense that this VB value can be extracted from VCC itself by putting a voltage divider. That is the fundamental idea of this voltage divider biasing.
Okay.
That is, from VCC, you will have this, this VB will be actually VCC into R2 by R1 plus R2. So that in this voltage divider biasing, you have only one power supply needed.
Okay, got it. Yeah.
Otherwise, the things are the same. The analysis, the function of the circuit, everything is the same. You Tevenize, find out that all those things, that is the same. So understand what is DC analysis, AC analysis. So this bias resistors, collector resistance, emitter resistance, all these 4 resistors are needed for setting the DC voltage and DC current. And what is this DC voltage and DC current that we are talking about is this VCE, IC. So this VCE, IC, that is the operating point. So by properly choosing the values of this these component values R1, R2, RC, RE, we can fix this operating point such that the transistor is in the forward active region, which makes sure that we are able to make it function as an amplifier. So these are for the fixing the operating point. Now we in addition, what other components we had is these coupling capacitors at the input and output, and the bypass capacitor. Input and output coupling capacitor is to block the DC, and this is to bypass the AC, the CE, because once this AC gets bypassed, no, you will not have, otherwise this drop across RE will reduce the AC gain. If that RE also is prominent or in the circuit. But once we make sure that CE is high enough, so that the impedance is, I mean, the entire AC bypasses to this ground, we will not have any drop across this RE, so that that much drop in the AC gain will not happen. So that is made sure by this CE. Okay, so CE helps to I mean, maintain the AC gain. Otherwise, if something flows through this RE, that drop will reduce the AC gain. And these two blocks the DC component. So at exactly the collector terminal, we will have both the DC component of the output and the AC component. And what we need is only if I provide some AC signal here of peak value, some 50 millivolt or 100 millivolt, and if the amplification factor is some 10, what I need to get here is 1000 millivolts sine wave. So that will not have any DC, and that is taken care by this CC. So conceptually, what you need to, as a whole, the entire picture that you need to learn in connection with the common emitter amplifier is, you understand the DC analysis, the AC analysis, the small signal analysis. Then what is the small signal gain minus GM/RC VI? What is this GM transconductance? What is that IC by VT? Then I think as he's asked that RL, it was a difficult question, but we wanted you to somehow explore and do it. That is the case with the load resistor. They're asking for the small signal gain. So that I told you, once this VCC is set to 0, RC will become parallel to RL. So that will be minus GM RC parallel RL. Okay. Then What else? Yeah, common emitter as such. This minus indicates it is an inverting amplifier. That's it. Now you need to you are going to replicate this common emitter amplifier one more time, so that you will have a matched resistors case, and we talk about that differential amplifier. Differential amplifier is where we have to, whatever is in common between the signals, that needs to be eliminated, and only the difference between the two input signals needs to be amplified. So differential amplifier, later in your higher term, when you learn something about the instrumentation amplifier, there you understand that the fundamental circuit inside that instrumentation amplifier is a differential amplifier. This operational amplifier, etc., also it is a differential amplifier inside. So here we had to the base terminal one input. So if you try to recollect that lecture on the differential amplifier, one more thing we are one more this side we are replicating this. That means this part, this transistor RC RE. Similarly, this side RE, and everything we are ensuring that this RC and this RC are matched. Everything is perfectly matched, etc. Then we are feeding one input to this base terminal, and to other transistors base terminal we feed the other input. So V1 and V2. So anything in common between V1 and V2, anything in common between V1 and V2 means mathematically, can you just tell me what will that be? If it is the difference between V1 and V2, we can understand. So the differential amplifier ideally needs to amplify the difference between the input signals. So V1 and V2 are the input signal, means I can write it like this. The output of a differential amplifier is AD BD plus AC BC, where this is the differential mode gain, and this is the differential voltage. So this will be V1 minus V2 or V2 minus V1 accordingly, and this is the common mode gain, and BC is the common mode signal. So can you just tell me, this is obvious, the difference between the signals VD is V1 minus V2. What will be BC?
V1 plus V2 by 2.
Average V1 plus V2 by 2. Okay, so this will be the output of the differential amplifier. And
But ma'am, can you tell me in this a little, like explain this, how this is?
Yeah, that's what you just yeah, so instrumentation amplifier, I can't tell it right now. Maybe I can tell it in this way. So instrumentation amplifier, you just see, I will just try to make you understand. So instrumentation amplifier, you will be learning it later. There it will be able to amplify the difference between the input signals. Okay, so differential amplifier, what we want is, we don't say for example something common between the input signals, practically I can say you the noise. Okay, so the noise needs to be eliminated. We don't want the noise to get amplified, but the information, the difference between the two signals, that we want it at the output. So differential amplifier will have to amplify the difference between the input signals, but it should eliminate the noise. So talking about, for an ideal differential amplifier, the differential gain should be very high. So ideally it should be infinity. And common mode gain, since we told that ideally it should eliminate anything common between the two input signals, so it should not provide any gain for the common part of the two input signals. So the gain provided for that should be 0. So AC should be ideally 0. AC is the common mode gain, should be ideally 0 for an ideal differential amplifier, and the differential gain AD should be quite high, very large. That means ideally infinity. And in general, the output from a differential amplifier, it will be equal to AD into VD plus AC into VC. That means VD is the difference between the two signals, and VC is the common what is common between the two signals, two input signals. So that will be V1 plus V2 by 2. Okay. Now, if you talk about any differential amplifier, that parameter something like that you see in the data sheet is CMRR, which is called as the common mode rejection ratio. Okay, so common mode rejection ratio is actually the ratio of this differential gain to common mode gain. Okay, so this in represented in dB will be 20 log AD by AC. That will be CMRR in dB. So otherwise it will be of the order of, if it is not in dB, simply this ratio expressed in this ratio, it will be very large value, some higher powers of 10, some 10 to the power 5 or so. Okay, so larger this value, good is the differential amplifier. Okay, and you can go back and search for this differential amplifier ICs, and there in the data sheet you will see this parameter CMRR. Okay, so now again that basic building block, no, this one, this was your differential amplifier. Here you instead of that 2 RE, here you what did you have here? Current source, correct? Do you remember this one?
Yes, ma'am.
Then coming to this discussion to current mirror, how did you do? How will you realize this current source?
It will be 2 I naught.
That will be 2I naught. I'm asking how do you physically realize, design the circuit for this current source. Even in your ESTC, you were solving lot many numerical problems where using this current source. So, what will be the actual circuit inside? How can you design that current source? What did we do here? If you try to recollect from the lecture,
Ma'am, I didn't get your question.
how will you design a current source? See this sum here. If I represent a current source of value I or I naught or whatever, okay. This say for example I naught is 5 ampere, a current source of value 5 ampere. Okay, so what will be the circuit inside? How will you design a current source?
I was saying about IE1 plus IE2 will be equals to 2 I naught.
I just want you to try to recollect the current source and current mirror lecture. I'm just trying to lead you towards that. In the current mirror circuit, what did we have? What connection did we have, and what does that mean? Current mirror.
Madam, voltage by resistance.
No, no. Did you see something like this?
Common base.
correct? What is this? Hmm?
Short circuited, is it?
Why is that done?
Same VB, uh, or maybe same current on the both side, right? IRF.
Oh,
No.
no, why is that base and the collector being shorted? And if that is done, can you just tell me that particular transistor? No, that means the one which you see on the left hand side, in which what to say, in which region
Common
of
this
operation it would be? In which region of operation it would be?
forward active region.
How will you say that it's forward active region? Is it forward active region?
Maybe we are making VC and VB same, because
See, base emitter junction is forward biased, collector base junction is reverse biased, that is your forward active region. Okay, that means base emitter junction is forward biased means what about the relation connecting this VB and VE, which should be greater?
It should be greater than.
Correct?
Yes, ma'am.
Then collector base junction should be reverse biased means
VC should be greater than V. Okay. It should be then VB.
okay.
VC should
Now,
be greater than.
okay, now in this case, how will it be for this transistor? Will this be
Uh,
satisfied?
I don't think so because like this VC is equals to VB, right?
Huh. So it is not in the forward active region as you said, correct?
Yes, ma'am.
So this transistor will be always in the saturation region actually. The
What does it mean by saturation?
this is wait a minute, this transistor, this particular connection, no, the short between the collector terminal and the base terminal, this is actually called as a diode connected transistor because the three terminals is for a transistor, and by means of this short you are in effect making it as like a just like a two terminal, so two terminal which is here like a diode, so it is generally referred as this connection, no, it is called as the diode connected transistor. And this transistor which is diode connected will be in the saturation region. Okay, so that means it acts as a closed switch. So here if you design the circuit, you had seen here this value of R will determine that mirror current. And as you see, when you the one another point done is this stages here, this is stage 1, stage 2, stage 3, etc. How many stages you have, say n number of stages, this here the base current here should is actually getting feeding the base of the this mirroring stages. Okay, so as you increase the number of stages, this I naught will slowly reduce from actually the I reference. And how it happens I will show you. So maybe that point we can do through some numerical example. So conceptually, you tell me the points that you need to understand in connection with the CE amplifier, the differential amplifier, and the current mirror is okay. Means I can take one or two examples from each of these topic and solve it right now. That will help us. Is that okay?
Yes, ma'am.
Yeah.
Yes, ma'am.
So maybe through solving those, I will. So common emitter amplifier. So are you okay with finding out the operating point, or should we have one numerical problem on that? Finding this VCE, IC operating point. I don't get response from you. Are you able? Sorry.
Can you repeat your question again?
Should I consider one numerical problem on fixing the operating point? That means you had Thevenized the circuit, find out this input side, and then you find out the output side and find out the values for this VC and IC. VC, IC is the operating point, right?
Yes, ma'am.
So are you okay with solving those
Yes, ma'am.
everyone, or should I? We can consider only the amplification part, signal part, no, right now in week 8. Week 7 was that fixing the operating point. So are you, everyone is okay with that? I mean, I will just tell you what we did, correct? If
Yes, ma'am. I am okay with it.
RC, RE, R1, VCC, R2, ground. So we by thevenizing the circuit, we had this VB as VCC into R2 by R1 plus R2, correct? Then VB on, we know it was given to be some 0.7
VB
volts.
minus
So
0.7.
VC you have found out. So VE you can find out, because VBE is VB minus VE. So VE will be VB minus VBE. Okay. So you so once you know the this if we consider the case beta is large, beta is equal to infinity, then if you know VE, IE will be equal to VE by RE, correct? And
Yes, ma'am.
IC will also be approximately equal to IE, because I beta is infinity means IB will be 0. All those things we have found out. Then once we have found out this IC, you know the drop across RC, ICRC. So that subtracted from VCC. So VCC minus ICRC will give you the collector voltage VC, and VCE will be VC minus VE. So these were the things that we were doing. Now, uh, about the small signal gain. So if you have that small signal gain will be V naught by Vi will be equal to minus Gm RC. Other than that, what did we see? Yeah, only these two things we had seen. And again, maybe transconductance I will just keep.
And there are some questions in week 7 practice assignment where
Okay.
VC is not given, but they were asking about VC. Like VCC is not given, and they were asking about VC. And when I watched the videos, I don't know from where ma'am is writing the VC as 10 sometimes or sometimes 12, but it was not given there.
In practice assignment,
Yes, ma'am.
can you just tell me the question number?
Yes, ma'am. Give me a minute.
Ah.
I think it is the last term maybe video you upload. It was uploaded from your voice. There actually that value is not given in the problem, but it was added.
No, no, you are asking in the practice assignment or in the some numericals in the lecture.
Right. It's possible to check. I have to check the videos. Is
We're talking from the video.
right. Video solution was uploaded for that week. There.
Oh, practice
Ma'am,
assignments.
practice assignment question number 9.
Mhm.
Wait a minute, I will just go back and question number 9. Okay.
Like first question is about ammeter, but there is a question about VC also. But for that VCC should be given, but it is not given.
Question number 9.
Yes, ma'am.
Wait a minute. I'm just taking the.
Yes, ma'am. VCC is not given here. And if we are using the
No,
VCE
this
thing,
is see the now in A means here
yes,
this
ma'am. I tried like that also, but it is not giving the correct answer. Then.
is the circuit not appearing for me, or in the portal also it's not visible. It is with regard to the previous
No, ma'am.
circuit
There is no
itself.
circuit. Ninth question.
Oh, even in the circuit also it's not given, and in the question statement also. Yeah,
Yes,
this,
ma'am.
this would be missing. And this I will check. None of you
Yes,
have
ma'am.
pointed it out. This VCC should be given.
Yes, ma'am.
No, you can't do without that. This was a mistake then. See,
Also,
I think in the question statement it was missed out.
yes, ma'am.
Yeah,
Also,
yeah.
ma'am, in like there is one more question
In
like
the
this.
solution, in the
In
video
that,
solution PDF that he was talking about, what value it was given, that was the value for VCC actually. Not that we are assuming or some reason for that, nothing like that. It was a mistake. VCC should be given.
okay, ma'am, there are 3 questions like this of BJT.
Here in the practice assignment.
Yes, ma'am.
No, no, this ninth question you're talking about is actually with reference to this circuit which we saw right now, this one. These are
Okay.
the same, I mean, what to say, common data questions. Okay.
Yes, ma'am.
With regard to this circuit, you're asked this BE, IE, IC, VC, VCE, then to check whether it is in the active region or not. So just now I told you, no, base emitter junction should be forward bias, collector base junction should be reverse bias. So you check with those potentials of those terminals, and accordingly you see that this base emitter junction is forward bias and collector base junction is reverse bias, and if that is the case, you say, yeah, you conclude that the transistor is in the forward active region. So that is this eighth question. And ninth question, the values being changed right now, correct? Beta 100 VB, VB RC 2 kilo RE5, now the values are changed. You can see here the values changed with respect to the previous case. So accordingly, how this parameters again, the values vary. So that
Okay, ma'am, get it.
concept understanding. But VCC should be given. This was by mistake, not given. This I will update in the portal before your end semester or whatever, so that you need not while revise again get confused.
Okay, ma'am. By the way, in that video, practice assignment video, ma'am took 10 in first question and 12 in second question.
First question and second question means what? Here with respect to this
Uh,
question.
in which the circuit is given, in that VCC ma'am took it as 10 volt, and in
Yeah,
second
yeah,
9%.
yeah. In the first question, in the sense, we're till eighth question, and second means you mean the ninth, correct?
Yes, ma'am.
That's what.
In
Yeah, that's what. This is for the understanding of, as I told you, by properly choosing the BCC value R1, R2, RC, RE, we are setting the operating point, right?
Yes,
So by varying those values, these values can also vary. For that, in the second case, now in A, the values are varied, including VCC also. That's why maybe in the first case it would have been some 10, and in this other case it would have been 12. Okay.
okay, ma'am.
So by properly choosing the circuit values as well as the VCC, you are setting the DC voltage and current. So these two were with some set of values for the first case, you find out VC, VE, IC, IC, etc. Those parameters. Then now the second set of new values. What are the these values again? That is the thing. So this I will note and update.
And also, can you check 22 to 26 question?
22 to 26. Let me just see what is the question.
Because I'm getting different answers. Even I tried solving 2 times, even more than that.
22 to 26. Wait a minute.
আমার ঠান্ডা লেগেছে, আমি খাবো না। আরে একটা খাওয়া কেন 50টা খাও? জানি না, সবেতেই প্রিজারভেটিভ ছাড়া হয়।
Arnav, mute yourself.
Yeah, I will just check, and if any discrepancy found there also, I will just update. Okay, 22 to and 26. I will just see.
Yes, ma'am, I checked
For
it.
what about others for 22 to 26? Are you also not getting the same answer mentioned in the portal? For others, 22 to 26 from the practice assignment, week 7. Do you remember? Have you tried solving those? Right now you are in week 8, so you should have come across these questions, right? No, I don't get any response from you. Okay, anyway, let me check and let you know, okay?
Okay, sure, ma'am. It will be 1.
Find V naught. In a differential amplifier, consider that input signals V1 is 0.5 volts and V2 is minus 0.5 volts. Find the output of the differential amplifier.
It will be 1.
Yeah, so here what do you see? The VD, you will be having the difference between the input voltages, which will be 1 volts, and VC will be 0. So you will have V naught to be simply equal to AD VD. Correct? So it will be directly the difference mode gain. Correct? Now if you consider, say for example, V1 and V2 equal to 1 volts.
Then we have to find V output. Then it will be 0.
Then what will happen? Will it be 0? Here V naught will be again equal to AD VD plus AC VC. So here VD, which is the difference between the two signals, it will be 0, and VC will be
VC will be 1.
1. So V naught will be
1.
the direct measurement of your common mode gain. Correct? So this is to just to typical values of your input voltages V1 and V2 to understand conceptually the differential amplifier. In the first case, you had the two inputs to be different, okay, and the output is the direct measurement of the differential mode gain AD. And in the second case, you have both the input signals to be equal. So there, it is the common mode gain will be the measurement of your differential amplifier output. I'll just take an example for the current mirror. So just to understand that what Mavish was asking, no. So this is the once again this is that basic current source circuit. Okay. Uh, and your reference current is like this, and this is your mirrored current. So I reference it would be VCC minus VBE divided by R. So I reference is the current flowing through this RC. That will be this potential VCC minus this is actually VBE by R. Now, if you have mirroring stages, the circuit will be like this. So this will be the mirroring current of the first stage. And here we have that. So actually what we ideally what we have is I1 should be equal to I2 should be equal to I3 should be equal to, and we have n number of mirroring stages. Everything should be equal to the same value. I is this current. What do you have here at the collector of the first terminal? This is I. Okay, so this should be equal to this I. Now maybe here I can write from my reference if I am reaching this node from my reference this flow as I, and this may be some other maybe I prime or something like that if we choose. Okay, so what do we have at this this node is I reference is equal to I plus I prime and what we have between the base currents, the relation will be IB1 equal to IB2 equal to IB3 equal to etc. equal to IBN equal to what is this IB1, IB2 etc. in terms of this I is actually the collector current. So what is the relation connecting collector current and base current? IB equal to
They are same.
IB equal to no I'm asking the relation connecting collector current and base current. IB equal to IC by beta, correct? So this is our IB1, this is our IB2, etc. So what we have is this will be equal to I by beta. Agreed? This I is this collector current. This is the IB1. So
Okay, ma'am.
so what we will have for this I reference is I plus I prime. So I plus this will be I by beta plus I by beta plus etc. How many stages you have? Those many I by betas. Then so that will be I plus if you have n stages, so n plus 1 into I by beta. So that will be I into 1 plus n plus 1 by beta. So current supplied by this first transistor IB, I reference by 1 plus n plus 1 by beta. Okay, so this if you substitute, you can see that you will have that if n is very large, accordingly you see here that will have that error in the mirrored current. Somebody has asked, yes or no?
Ma'am, I am not getting that. Can you go to the earlier page?
Yes.
There I and I dash means I will be still there because that will be the saturation, right? That you're saying that it will go only the current pass the current through the that branch, the short circuit branch. So will there be still current through that saturation branch? That I mean NP, the base,
You are asking I prime.
right? I prime will be there because
Okay.
that's short circuit, but I which is coming towards the base then through transistor.
Yes, I will be there.
But will it pass through that base?
Pass through what?
Pass through the transistor and the base and then emitter down, it will go down because that's why it should, it is saturated point, right? Yes.
Saturated point. It will flow through
Both the
close to the
branch,
ground actually. This will act as a close switch, this transistor. So this I will flow to
this
the
will be
ground.
reverse bias, right? I mean, sorry, yes, it will be reverse bias, right? That I which is
Which
passing through
one
that
is reverse bias? This I
left one.
told you this will be in the saturation region. So this will go to ground. This
Okay, directly, but it will pass through the base and then the emitter, right?
I prime will go to base. This one.
Okay, okay, but how it will be then the C to E it is coming, it has to go through that the middle P junction, right? Means N P N. So P it will pass still through the P, that I.
NPN, you're asking which current? Can you just tell me once again? Will yeah, okay.
That will be how it will be passing through that because that is a
I think
saturation.
I think you are taking I reference is equal to I. That is the confusion you are having. I think
Yes, I reference equal to I plus I dash, right?
correct.
So I dash will be coming. I understand that is a short circuit that we make that will be crossing the. But then how the I is coming there? I was thinking the I reference equal to I dash means there will be no current through the I branch. Means the left side. Maybe I'm not clear on that. Maybe you cannot annotate. I'm
No,
just
no,
asking
this
the
is
two
the
branches.
this
It
is
will be
that
divided in two
this is
circuits.
if you consider this circuit it was clear.
Yes, here may be doubt. I have the I
No,
reference.
this I reference only we are doing. I mean, this in the second circuit, this I reference only we are actually doing by means of this resistor. So here you didn't have that doubt, right?
Yes, current will pass through that short circuit branch, and that what about that? The current through the transistors.
Current. No, why
It,
do you say that this current is zero? I don't understand. You are telling that this to be zero and only this
yes,
passes.
still
Why
there will
this
be
to be
current. You are
zero?
saying. Okay. No, I misunderstood. Then it will be their current also.
Yeah.
I thought there will be no current because that is the another part is short circuited. No resistance, nothing. Right? No
No,
B.
no, no, no. Here, by means of the short circuit, you have VB equal to this, what to say,
We are making VB equal to VC right there.
VC. Ah, correct.
So there will be the current only. I thought that there will be no current through the transistor
No,
branch
no,
then.
no. There will be current here also.
Oh,
So that I told. This is the single building block actually. This one, this particular point. This here. I mean, this is the reference current, which we what to say designed by means of this resistor here connected at the collector. So that value will be actually this VCC minus the VB value of this transistor. Now this is the reference current, this is the
hmm.
mirrored current. This I naught should be equal to this I naught ideally should be equal to I reference because that's why we call it as the mirrored current. Exactly, this current is mirrored here. Now,
How we can make the mirror current means is it is it another source is coming from that current? Well, that I am not clear also from the lecture that I zero is how it is coming. That is Is it the same as I reference? But how it is? What is the source? Is it come the common voltage source?
That is why means of this diode connected transistor we had seen how this happens. If you try to see, uh, in the diode, if you had seen that what did we have, that diode current, it was exponential, that VBE. Do you remember?
Right.
And here also, this is this, if I label this transistor as Q1 and this as Q2, Q1 is diode connected.
Right.
So you can just relate this current with respect to the diode current I am talking right now, e raised to VBE by that VBE. Where is the for that here for this transistor it is the input current. So accordingly you will have this to be by means of this connection, it will be equal to this I reference, correct?
So is it as it is there coming common base? That's why it is dragging the current, the same current. Is it?
Yes.
Okay.
Okay, now this is the basic building block. Now here we are replicating the mirroring stages, okay, to multiply the current. So these are the replicating stages I have, the mirrored stages. So this is stage 1, stage 2, etc. So accordingly I have labeled the currents I1, I2, I3, etc. So for just to make you understand for that one assignment question, to make you understand, as the number of mirroring stages increases, the mirrored current will have an error. It will not be exactly equal to I reference. And why it will not be exactly equal to I reference only, I am right now talking to, trying to explain to you. So here I have just shown you that replication here and the same circuit. At this node, this red color which I have marked here, you know that I reference is KCL will have I reference equal to I plus I prime. And ideally it should be, these mirrored current should be equal. I1 equal to I2 equal to I3 equal to, I have n number of stages. So that should be equal to the reference current of the first stage, which is the collector current. So that will be the I. Okay, this I. So that here what I have written, I1 equal to I2 equal to IN equal to I. Then IB1 equal to IB2 equal to IB3 equal to IBN. So that will be IC by beta. So IC is I. So I by beta. So that is equal to I plus I by beta plus I by beta plus I by beta. So what we will have is I plus n plus 1 I by beta. So if we try to derive the
So what is that I?
relation connecting I reference and I, we will get this I as I reference by 1 plus n plus 1 by beta. Okay. So if you substitute some n is equal to 5 and you see randomly you choose some I reference value, you
Ma'am,
see
how
what
we can
for n
calculate
is
the I first? Means it will I reference is given mostly, right? So how we can calculate the I? First we need to know the I, right? Then
this I plus I prime, correct?
correct.
That is what we are here we have written. I
Um,
prime will be how many? I prime is this one. I prime this current is actually driving the these mirroring stages.
Now,
I
how
is
may I
this one.
calculate the I value or I dash value? I dash value is the I by beta, but how may I know that what is the I value? What
I value is what I told you. This one, this VCC minus this VBE by
uh,
R. Here there will be a
R
R,
resistance? Okay.
correct? This
Mm-hmm.
one.
Okay. Okay. Now good. Yes. Got it. Yes.
So here you choose a reference value for that I reference, and here you see the case for n equal to 5 and n equal to some 10 or 12 or 15. So you can see that the error in the case of n equal to 5 will be less than the case with n equal to 10 or 12. So as you increase the value of n, the error will be more, and that is mathematically shown here, or conceptually you can see that the base current coming here, no, that should drive the base of the remaining stages, and base current itself is small, correct? So that is the thing happening. Do you understand that point?
Yes, ma'am. I got.
This current here, it is equal to it is driving the these transistor here, because this is splitting here, this and this is actually the sum of all these, correct?
Mhm.
So this
Ma'am,
itself is
if there
small.
is any resistance, all the other next subsequent transistor like I1, I2, where is coming through, if there is any resistance, then
You are saying a resistance here.
right,
Ah,
then
that is a different case. Here we are just telling the what disadvantage of the basic current mirror circuit.
okay,
Correct? If you have increased the number of stages, then there will be an error. What you say is a different design.
okay, complex and maybe two.
Okay, so this is the mathematically for showing you that error in the mirrored current. So this was one of the assignment question we had. Then uh, wait a minute. Any other key point that you have? Are you able to solve the other questions on this differential amplifier? Because differential amplifier, if you see the assignment questions, that V1 and V2 no given. Uh, did you understand first the way it is explained in the lecture? That means what to say. You will have exactly ideally the same current flowing through on either sides, okay, but as you vary, it will steer to one side, that current. This is the differential amplifier. So this was your 2 I naught. So when do you have this here also flowing I naught and here also flowing I naught? When do you have this case? And when do you have the entire 2 I naught steered to either this side or this side? Can anyone of you explain that? I mean, when it is equally flowing on either sides and summing up here as 2 I naught, and when you have this entire 2 I naught on one side and it is 0 on the other side. I mean, the other transistor is off. Explain this, the differential amplifier operation. Can anyone explain? How do you have this I naught flowing on either sides?
That
You have that.
that I know it comes from VCC and
No,
other.
no. I'm asking with respect to the two input signals V1 and V2. You can have a large difference in the two input signals and small differential voltage. Correct?
Yes.
Yeah. Tell me when you have this I naught flowing on either sides and that summing up as two I naught and flowing towards the ground, and when you have say the entire this two I naught is flowing on. I mean one of the transistors is fully on and the other is off. When does that happen? In that case, is the one where we
Uh,
say that current has steered to one side.
if we input 1 is large or we input 2 is less, then like very less, then we input 2, that transistor will get off, and then first one will get stays turned on, because we have to make a balance of 2 I naught. Yeah.
It's not totally clear. Anybody else? First of all, have you gone through the week 8 lectures?
Yes, ma'am. But it's
Yes.
so confusing, ma'am.
I completely got confused. Lecture didn't help to understand the concept.
Okay, let me just see. This is easily explained here. I will just maybe share that. I will just search. Wait a minute. Or are you people having that the prescribed textbook with you, Sedra Smith? There it is very well explained. I am just searching for that to screen share and wait a minute. I will just locate that PDF. Okay, there. There it was some good typical values for this V1 and V2 taken so that you can understand that current shearing. I'll just
Can you tell me the book name?
microelectronic circuit Sedran Smith, the prescribed textbook.
Okay, ma'am. Okay, ma'am.
My this thing got updated and I don't know. I'm not able to locate it. Maybe wait a minute.
Do you know the page number? I have the book. I can open it.
No, no. I don't remember the page number. I am just trying. Wait. A minute. Yeah, I got it. But here it is. Okay, better I will share that in this thing because this is not opening. I think that is corrupted. I'm not. It's not opening that chapter. Okay, fine.
Ma'am,
So
tell me the page number. I will try to open
no,
it.
no, you open the chapter on the differential amplifier and you can see that is being explained. I mean, when you increase that voltage, no, when you make that variation, you can see that On one side the current slowly increases, and the other side it decreases, and at one point of time that will the entire current will be on one side, and the decreasing on another side, that becomes zero. So that we say that the current has been and steered to one side. You just press, if you have the PDF with you, you just press Control F and search the topics differential amplifier, and then come to that chapter, and you can just screenshot that page. It is
Ma'am, I'm sharing. Then
yeah, yeah, I will stop presenting from my side. You can share. There you can clearly understand. Yeah, Sonali, syllabus for quiz 2 is week 5 to week 8. Week 5, 6, 7, and 8.
Yes, ma'am. What I have to search?
Here you will have that what is the analyzing what is the this month potential at this common emitter terminal, no? Accordingly current will be getting steered to one side. You just move on the pages, scroll. This is BJT cascode. You go to the differential amplifier.
Later, maybe.
Later.
Section 8. Yes, after that. Current
It
figure
is.
differential amplifier just gone. Also. Differential amplifier, if you search, maybe.
These are the variants of the current mirror. You have to go for the differential amplifier.
Oh, okay.
If you type differential amplifier, maybe.
Yeah, that's what I told you. You just press Control F and type differential amplifier.
Here, what's the page? Here.
What is that sound being heard? Can you just mute? Yeah. Differential mode, common mode, gain signal, and then move on. Oh, this we have come to the open loop operational amplifier. See, maybe I can as I told you, I'm not able to take in my device right now. Something got corrupted and some updates. Some I'm facing the issue. Maybe I will share that exact PDF once I get tomorrow or so. Yeah, difference amplifier you have, but check with the BJT differential amplifier. There clearly that what to say, that small signal analysis also done. No, these are the operational amplifiers. No, I'm not able to memorize the question. I mean, what to say, chapter number, so that I
Chapter
can.
8, that is differential amplifier with current mirror load.
I will try it out.
Multi-stage amplifier. It looks like, ma'am, transistor is like a resistor. It can be connected it in between different circuit, and it completely problem get changed.
You are doing in parallel that lab also, right? I mean, electronics lab.
No, ma'am. I'm doing it next time.
None of you are right now part of that lab, electronics lab. None of you here are not doing that. Everybody is going to enroll sometime later. I okay.
Yes, ma'am.
Abhay telling he's doing. So you are doing some experiments. So there you will be able to understand something, right, out of the practicals. Yes, Abhay. Yes or no? Abhay Pratap Singh. I don't know why you are not taking the lab in parallel. Okay, no issues. I will just, I mean, ask the other instructor to this one share that this thing to you. I can today somewhat locate this PDF and share with him. So the thing is, uh, you had the discussion of that activity questions of week 6 with that TA, right? So he will be doing the discussion on activity questions of week 7 and 8, so that we are planning to schedule it on Friday evening. And Friday you have the morning, I think the other instructor would be taking instead of tomorrow, I think. Okay, and Saturday you have the session. So Saturday maybe he can do it on mock. Page 106 is starting for what? This one, differential amplifier. Okay, whatever. I have to first get the PDF from my side. I'm not able to locate. So there, do you see? If you have it with you, did you find the thing that I'm mentioning about right now? They will easily analyze that common emitter terminal. So accordingly, how the current is steering. I mean, the entire current is flowing on to flowing through one of the transistors towards one side, so that the other transistor is completely off. Do you see some V1 is some volts, the other is some -1 volt something given? That did you spot out, maybe? If that you were able to get, you can share that. That is the one I waiting for. Did you see something like that? Yeah, sure. This is what she has also shared. You can go to that page. Yes, we are able to see your screen. No, I don't think.
This is difference amplifier. Differential amplifier is later, after chapter 8
No,
or around that.
it's okay. It's okay. I will just locate it in my device, and I will ask the other instructor in the next session to explain to you. So what I was telling to you, the other session, was it helpful for you? The discussion on the activity questions of week 6. which you
Yes.
had with the TA. So he will be explaining to you again that week 7 and week 8, so that you will have it on probably on Friday evening. And the other instructor will discuss with you on Saturday probably the mock paper. So you will get the mock paper tomorrow for the quiz 2. So from the Laplace, you can expect the basic, I mean, Laplace of the this one. You all already had that week 4 part of quiz 1. So week 5, the application of Laplace in the circuits. So uh, so something from that you can expect. And this partial fractions, all those things also, where you use for finding out the response of that circuit, time domain response, so that you need to calculate the inverse Laplace transform. So all those things are part of week 5. So that is part of your quiz 2 as well. Then again, that properties in that, mainly the initial value theorem and final value theorem, that is again important. Mm. Then coming to diode circuits, the basic typical circuits that we are seen in the lectures as well as in the assignments, we had even solved in the live session. That means without first, whether it be positive clipper or positive clamper, without that external bias and with the external bias, something like that. So those basic operations you need to understand, and some basic circuits on with a diode, where you can figure out whether the diode is in the on condition or in the off condition. So accordingly, what will be the current flowing through the circuit, and what will be the voltage across the components in the circuit, whether if you have a resistor, what is the voltage across that resistor or something like that. So some simple questions only, just like similar to the assignments, you can expect in the QP. So do one thing. You just individually, if you have any particular doubts, you put it in the discourse. So I will ask the other instructor to, since you are not feeling confident especially with the transistor, I will just ask that transistor again, once again, to be dealt. This one, the differential amplifier that I am telling you, that steering part, that I will share with him. Mock paper also he will discuss, and that TA will be discussing the week 7 and week 8. So anything other than that, individually, if you have any doubts with in the assignment or conceptually, please tag us and put it in the discourse. I have already just noticed one query put by Tansil. I don't know whether he's there today, that I can later respond to him. We didn't get actually time. So anyway, we can respond to that. Tansil has put one query. So other than that, you can do. So diode, are you right now confident with clipping and clamping, then Zener voltage regulator, and that voltage doubler circuit? Diode circuits, are you finding okay with? The transistor is right now difficult for you.
Yes.
When it's mainly this 8th week.
Yeah, okay. So 8, I will just ask the other instructor to do once again. This, sorry, I'm this morning it got updated and I'm not. I have some issues, so I will just locate this PDF or this exact page. I will just ask him to explain to you. So, small change in this input voltages, and when you have a large differential input voltage, so how accordingly the differential amplifier functions. And when you have both of them equal, that means the common mode signal while applied. Again, these are the 3 typical cases that we have to discuss to exactly understand the differential amplifier. That means you have a small differential input voltage, large, then the common mode signal being applied. And I think accordingly only we have taken the assignment questions also. What is Prince asking? Please discuss how to draw the transfer characteristics of 2 diode. Sorry, Prince, draw the transfer characteristics of 2 diode means what? You're asking, given a transfer characteristics, how to design the corresponding circuit, is that, or? Prince, what you are asking? Yeah, activity you can have it in the separate session, Abhay. Yeah, transfer characteristics, and from that you are finding the circuit. Yeah, that also we can do. So I will just maybe I can ask the I mean, including some questions like this. I mean, this transfer characteristics and this one, some tutorial questions. I will just ask the other instructor to do. Okay. Partial fractions and all, it will be just like similar to the order of that equation, no, just similar to that, to the depth that has been discussed in the lectures and the assignments, that you can expect. Is two diode or more diode in a circuit, then how to deal with it? See, generally with the diode problems, when you have more diodes, which one is on and off, we don't know. In for certain questions, it is obvious with the configuration. This is forward bias, that is reverse bias. So which is on, which is off, we will be able to tell. For some other topologies, the things may not be obvious. Then we go with some assumption that this is on, the other is off, and or both are on, something like that, and we try to find out the voltage and current, and what you result in, if it matches with our assumption. Say for example, you had some you had assumed that that diode is on, and you try to calculate that value of that current and the direction. If it is not if it is contradictory, if the calculated values are contradictory to your assumption, then you go with some other assumption, something like that. That is the way with some diode problems, Prince. In every question, the things may not be obvious, but you need not worry. The diode problems are all simple only. You always make sure that if you are able to try solve the assignment questions, 2P would be easier, because always the assignment questions are generally made difficult than QPs, because that is for your learning. Yes, tell me.
Ma'am, I have not. I have a problem with how to draw the characteristic and transfer characteristic, not in the on-off type question.
When more diodes are there, how to draw the transfer characteristics?
Yes, ma'am.
You had such question in the assignment? I don't.
Yeah, not exactly, but I see some of questions. There are two or more diodes and in a circuit, and they ask for the transfer characteristic.
But I think those things will be more complicated for you. I don't know whether that you need to do, but as part of learning, we can anyway discuss. We had even not, but I think shunt clipper and all we had already in the assignment done with this transfer characteristics, correct? Other than that, do you mean it in the series circuit or what? When you the thing that you are mentioning, more diodes means what type of circuit it is? Series clipper or shunt clipper?
Ma'am,
Series clipper with more diodes, do you mean?
ma'am, it doesn't matter, right? It may be series or a shunt.
Shunt we had already done in the assignment. That's what I'm asking. That's why I'm asking.
It was there was a question from there a KVL will be violated, right? There was
Correct.
only one question.
Correct.
I am referring to the Hayat, which was the part of the ESTC. There I got a question. They asked for the transfer characteristic.
Part of ESTC.
No, no, no. In the
Oh, some
ESTC,
competitive exam you're telling.
sorry.
Sorry, come back once again. Which question you are referring to? Can you just tell me the question exactly?
Yeah, I will share it on the discourse.
In the discourse. Okay, okay, okay. For that, you want the transfer correct?
Okay, ma'am. Yeah.
That okay. So tomorrow, I think the other instructor session may not be there because we have some meetings on Thursday. So that's why he is having that session some other day. So if you have it tomorrow, anyway, you will get the intimation. Otherwise, it will be on Friday probably. Anyway, you will get the intimation mail and message accordingly. Before that TA session also, you go through the activity questions so that you can ask doubts to him and get it clarified. Activity questions of week 7 and 8. 6 is already done. Okay. And mock paper also, the other instructor will be discussing with you. Okay, so this you just remind me that differential amplifier that I will share. I will ask the other instructor also to explain to you that that will clearly tell, because that I liked actually the way it is explained in the textbook. No, so that we will do. Okay. Yeah. So we will be meeting Monday after the quiz. So do well. We will meet on next Wednesday. Okay. So all the best.